Fantastic. Thanks, Patrick, for the opportunity to present our research first and foremost. As you mentioned, the back catalogue of the Battery 2030 Plus Excellence Seminars is just a wonderful source of information, but I think inspiration for people as well. This covers so many different topics, so hopefully I'll be able to add to that. As you mentioned, so I'm based here in the University of Limerick. So I'll give a little bit of an intro just as a quick kind of sales pitch about what we're looking at here in the University of Limerick. The title, as you mentioned, is around Group 14 materials. So I'll talk about a range of the elements present within Group 14. And the beyond will be most of the talk. So we'll hint at some of the nice applications where we've looked at lithium-ion battery applications of these materials. But I guess for people who would be very familiar with that, is to try and move beyond to see if we have some other opportunities there as well. So my brief sales pitch for people who may not be aware, this is Limerick. If I can show the cursor here, is down in the southwest of Ireland. Very nice city for people to visit. And where we are is in the university, which is about 5 kilometers outside of the city centre. This building that I'll point out here is called the Bernal Institute. So that is where all of our material science research takes place. And we're very fortunate that we have this institute where we have all of the various components that we need to do really high-end battery research all under one roof. So we're very lucky that we have high-end microscopy and analysis suites coupled then with our electrochemical testing and material synthesis infrastructure that I'll kind of point through as I go through the presentation. So as Patrick mentioned, the AMPEiRE Research Centre, for people who are not aware, what we've tried to do is bring together kind of a critical mass of battery researchers and broaden the scope a little bit to include energy research as well. So you see that the battery heavy topics are up here in the top right. These are things like advanced lithium-ion battery development, high energy density battery chemistries, and obviously non-lithium. So that there are things like sodium ion, for example. So they all use the kind of key infrastructure that I've pointed out in the Bernal previously. We have a broader team that encompasses some of the broader energy related device research. So things like thermoelectrics, for example, piezoelectrics. We have nice research on electrocatalysis. All of that then is underpinned by this characterization equipment. So we have, for example, aberration corrected electron microscopy. We have operando X-ray capabilities within house, and we have high-end spectroscopy where we can do that all within one place. And then on the kind of broader side of things up here at the top left is around kind of the circular economy approaches. So we started to dip our toe in a little bit around things like materials recycling, second life applications, and obviously then on the kind of policy and economic drivers. Because as we've seen from the various talks previously in Battery 2030 Plus, the material science really is only one component of it. So I think it's a fantastic area to research in because by definition it is so interdisciplinary. So we need to have all of these different skill sets to contribute towards what we're trying to do. And this is just our little snapshot then of some of the activities that are going on here in the University of Limerick. So I will primarily touch on research that's going on in my own group, but I would encourage people to search through the AMPEiRE website, see all of the other various principal investigators. We have more than 20 principal investigators now within AMPEiRE, and they all have their own expertise that we're able to bring together. In terms of Group 14, so maybe just as a refresher to people, I'm sure we'll leave out lead down at the bottom just for many reasons, but just to give you kind of headline numbers around the materials that we have here. So we have carbon. Obviously, in terms of their ppm abundance as we go through, carbon is relatively abundant, silicon is significantly more, and then we have germanium and tin, which are present in the Earth's crust at about the single-digit ppm level. Now, people may be well aware that germanium is far more dilute in terms of its sources. So even though tin and germanium are comparable in the terms of abundance, their actual production values are much, much different. So I'll give it a little bit of a hint on that. Again, not going to touch too much on carbon. We could do 5 seminars back to back on carbon materials for energy storage. People are well aware, obviously, of graphite in its key role in lithium-ion batteries, and obviously things like hard carbon then within sodium applications. So it's the heavier elements that we're more interested in. So silicon is one of the many kind of holy grail materials that are spoken about in batteries, alongside things like lithium metal anodes, for example. Um, the key difference, obviously, compared to carbon is that we can access through alloying mechanisms much higher specific capacities than we can in carbon. So, for example, you can access specific capacities in silicon that are 10 times that you would see in graphite. As again, people are, I'm sure, very aware, these go through these lovely alloying mechanisms. So, for example, your fully alloyed silicon content here is up to Li15 Si4 at room temperature. But because the silicon is accommodating so much lithium, we have significant volume expansion in that active material. So there's been all sorts of sophisticated material design approaches where people have looked at nanowires, for example, which are a system that I will discuss in good detail today. Things like core shell structures, yolk shell type structures. And for example, when you go to nanosilicon with really high surface area, your SEI becomes an absolutely key issue in there. Okay, so there are significant challenges on pure silicon anodes that have not really yet been fully overcome. But the thing to say is that we shouldn't really think of these as almost silver bullet technologies. There are places for pure graphite anode materials, there are places for pure silicon, and in between. Germanium is a material that keeps bringing us back in because it has some very interesting properties. This paper that I show here is actually from a colleague who is in the Chemical Sciences Department, Ty Kennedy, who carried this out during his PhD over a decade ago. And what he found during this study was that if he took a germanium nanowire electrode, what would happen during lithium-ion cycling is extremely long cycling stability. And what he found was there was this really nice porous network that was formed through material restructuring of the germanium. So germanium is a very robust material in terms of long-term cycling stability. And then with tin, again, tin has found applications both in lithium-ion and sodium-ion applications. You'll see straight away from comparing it to the rest of the group 14 elements that it is significantly more dense. Okay, so we're up here about 7 grams per centimeter cubed. So from a volumetric capacity perspective, tin has some clear advantages there as well. And for example, tin is active in sodium-ion cycling, whereas silicon is not. So what we have within this group is we have some nice overlap in properties, and then we have some interesting kind of material linked properties, like, for example, what we saw in germanium. Just to flag, I mentioned around the production discrepancies here. This is data taken from an EU website, which is really useful. It points out the kind of production values for different materials and sources of them. For example, natural graphite is about 1.72 million tons per annum. Silicon is about 5 million tons, depending on the quality. So there are a range of different silicon qualities. Germanium globally is about 150 tons per annum. So you can see that the amount of germanium that is made, despite it being a really important material, for example, in fiber optic cables, is far more limited compared to tin, which is up around 389,000 tons. Okay, so we're talking about 3 orders of magnitude difference between germanium and tin. Looking then at the kind of charge storage mechanisms in group 14 materials, you'll see here, these are our various charge carriers that we could consider. So we're looking here at, say, the group 1 elements, so lithium, sodium, and potassium. And then we've our group 2, just to complicate our lives a little bit, we could look at magnesium or calcium as well. You'll see the ion sizes as we continue on. The smallest ion is magnesium, then it's lithium, calcium, sodium, and potassium. Okay, so the kind of charge storage mechanisms that we can unlock will be very much linked to the charge carrier size, firstly. If we look at this table here, so that this is to be taken intentionally with a pinch of salt. Okay, so I mentioned this as a caveat that the capacities that I show up here, they're all in terms of milliamp hours per gram. They are based on the phases that are shown below. Okay, so in this case, some of these are not easily accessible or may not be accessible at all. So if I flag this sodium silicon system here, you'll see that the theoretical capacity, which would be quoted in any number of papers, is linked to the formation of this specific Na 0.76 Si phase. But it is extremely challenging to form that electrochemically in the first place. So what you can think of this is almost as a roadmap where we would try and access some of these higher capacities. So for example, up here in the case of magnesium, if we could form this magnesium 2 silicon alloy here, you could boast really, really high capacities here. So this would be up around 3,817 milliamperes per gram. Some of the headline ones here, again, that value I'm sure people are very familiar with. That's the theoretical capacity of lithium storage in graphite. Silicon, again, that 3579 is based on this phase down here. You see for germanium, we get up to 1,384. And again, for tin and lithium, we can reach nearly 1,000 milliamperes per gram. Okay, so this is kind of the playground where we're working with all of these different group 14 elements and then trying to investigate these various charge carriers and what might be possible in these systems. Just to give a little bit of an alternative idea here. So people are very familiar with these lithium-ion systems. Okay, they're in every laptop that people are watching this on right now and in phones. The key selling point obviously is on the energy density. So they're a super mature technology. We know about the charge storage mechanisms. They're high performance. They're viable. The sustainability, particularly linked to the cathode side, is an issue. So even if we neglect the cathode for a minute on say the transition metals, we can just look at the charge carrier abundance here straight away. So we have lithium is present as 0.002% of the Earth's crust, whereas if we look at something like sodium, it's already at 2%. So we have, even just from the charge carrier, we have significant material scarcity. On the opposite side of that dichotomy then is the sodium ion or more sustainable batteries. So you could look, for example, at sodium as your charge carrier. You're immediately at 2.4% of the crustal abundance. Not quite as established charge storage mechanisms. So again, even within hard carbon, there's still ongoing debate in the literature around the exact charge storage mechanisms in hard carbon. But what you should be able to do, at least conceptually, is try and get sustainability of your charge carriers and also your materials. So the idea here is with an inbuilt energy density penalty because of the reduced capacity of the materials, you can increase the sustainability. So you'll see these two kind of emerging paths or diverging paths where the more sustainably focused battery chemistries are looking at sodium ion, for example, and then the high performance ones like in EVs are focused on lithium. What I'll show is the kind of final section of the talk today is around the idea of dual ion batteries. So the idea here is that you would essentially base this almost around a sodium ion chemistry. And what you would do is incorporate some charge capacity boosters into the electrolyte. So the idea here within a dual ion system is that you would have an electrolyte component that contains additional lithium ions within the electrolyte. So what that can hopefully do is basically broaden out this table that we see here and allow us to unlock some new charge storage mechanisms and hopefully boost the performance to kind of find a Goldilocks zone in between sustainability and energy density. So this is a perspective article that we published 2 years ago, which was focused primarily on silicon nanowires. But the idea here, it can be translated to germanium or tin, for example, within the group 14 materials. So we had 3 main sections within this perspective. So we were looking at these silicon materials for as a model system. We were looking at them obviously from a practical lithium-ion anode side and for beyond lithium-ion batteries. So as I said, 80% of the results that I will show today are from this section up here. I'll show some nice broader examples from the University of Limerick around the model system and kind of the practical side of things. Why they're so interesting as a model system, silicon nanowires specifically, is you can use them very easily to track things like SEI composition. So you can look, for example, at the structural evolution of your silicon active material as it's cycling. And one of the reasons for that is you can very easily grow these silicon nanowires directly from a current collector. So what that does is it removes the impact of any binders or conductive additives. So essentially what you're seeing in that is just the silicon itself. So as I showed in that example previously for germanium, you can track the, say, the morphological evolution of the materials as they cycle. On the practical side of things, there have been a number of different approaches to try and modify these silicon nanowire systems for practical applications. So this has grown from a really rich literature around CVD growth of silicon nanowires, but one of the main challenges with that was getting to the areal capacities that you would need in a practical system. Okay, so we need to be up around 3 or 4 milliamp hour per centimeter squared at least in terms of those systems. And if you grow a very low loading of these silicon nanowires, you just won't reach those. Some of the opportunities here are around modifying the current collector, for example. So increasing the surface area of the current collector and then growing your nanowires up here, as we have tried some approaches in the University of Limerick in the past. And we've also used these nanowire architectures as hosts for amorphous silicon deposition. So this is the example that I will show in the next couple of slides. One thing to notice on these current collector modifications, and I think the literature has caught up to this, is any inactive mass that is added to the system will by definition dilute the energy density that's possible. Okay, so if you have a super complicated 3D architectured current collector, you may have completely diluted any of the energy density benefits that you might have gotten from adding in silicon. So what you need to do is have these lean systems where you minimize the dead mass that is in your system. And one way of doing that is almost in between. So it's coming up with these silicon nanowire graphite composites. So the approach here is as a stepping stone towards the 100% silicon anodes. So what you can do is, rather than growing these wires directly from the current collector, is you can grow the wires from graphite. So this is a nice, reasonably high surface area material, and it also has the benefit of being electrochemically active as well. So you can potentially tune the composition of your silicon graphite anode materials to get the desired performance and mitigate some of the really excessive volume expansion that you would see in pure silicon anodes. In terms of beyond lithium-ion development, this is the work that I'll show in nice depth, is around using the fact that these materials are lithophilic to try and guide lithium plating and stripping within metal anode systems. One of the model system type papers that was published, so this was carried out by Abhinaya Sankaran. This was within a Horizon 2020 project, which is finished, called SciDrive. It's the first of the two Horizon type projects that were coordinated by Professor Kevin Ryan here in the University of Limerick. And what Abhinaya did here is she used these core shell type nanowire kind of model system. So this dark core that I'm showing down here at the bottom, this is a copper silicide nanowire that we're able to grow nicely within the lab. And then these had amorphous silicon deposited on top of those. Okay, so these again are a nice high surface area model system for us to analyze the SEI composition as a function of the electrolyte composition. So what Abhinaya did was she performed XPS analysis then with depth profiling and basically was able to link the chemistry of the SEI to the decomposition pathways of the different electrolytes that were shown. On the complete opposite side of things, so this is looking at the upscaling of these materials. So again, for people who may not be aware of the types of Horizon Europe projects that are out there, the idea essentially is you bring expertise from all around Europe, from industry and academia together. Within the University of Limerick, as I said, we're coordinating the project here. We're responsible for this silicon graphite anode material. So we were able to form this routinely at gram scale, which for us was lots to be able to test the materials fundamentally, but to try and test this in terms of moving up the TRL scale, we needed to work with partners. So we did that by working with Temek, who are based in Poland, and they developed this reactor design for us, where we were able to increase from the gram scale up to the kilogram scale. So again, just to give you kind of a highlight idea of some of the results here, these are images taken from different zones of the reactor that we had. The key thing to just point out here is that the silicon content in these three different zones are reasonably consistent. So the idea is we wanted to really tune the material that we were able to form. So you'd see two different generations of materials. We have our generation 3, which is 30% silicon content, and our generation 2, which has about 25%. And the idea here, this is just showing the kind of fast cycling test, is just to verify that you have this dual active composite where you have silicon and graphite, both of which contribute to your capacity. Again, significantly boosting it beyond what pure graphite can give us. So this brings me on to the beyond lithium-ion part of the talk, which, as I said, is the main meat of the discussion. So with all of that in context, that is the main type of research avenues that people are looking at within the lithium-ion space. Okay, we can use these group 14 materials in different approaches. So you could think of using them as hosts for lithium metal batteries. So I'll show that in a second. And we could also look at them in these dual cation batteries that I mentioned before. So the idea here would be that you would take essentially, as I mentioned, almost like a sodium-ion cell, and then you would just incorporate lithium here within the electrolyte as a capacity booster. So these types of approaches, they're now being worked on in the lab based on a project that's funded by Research Ireland, which is basically our Blue Skies research funder here in Ireland. So like all good research, this kind of started through a eureka moment in the lab. So what I'll show first is this is a carbon paper substrate. So you see Saeed Abdullah Had, who was a PhD student while this work was being carried out. He's now a postdoc in the group. Up here, that is a carbon paper. This is molten lithium, which was done within a very low oxygen content glove box for safety. What you can see is that this is a super lithophobic surface up here. So when you try and incorporate that lithium metal into the carbon paper, it just does not infill. We had all of these established synthesis routes to grow these nanowires onto various surfaces. So we took the carbon paper, we deposited tin onto the surface, and then we grew various nanowire compositions on top. So we had silicon nanowires, we had silicon germanium, and then we had germanium at the end. And as soon as you try and incorporate molten lithium onto those, what you'd see is these are super lithophilic substrates. So what happened is that immediately infilled. What I would say with these is that they're reasonably thick, and the amount of lithium that is incorporated is extremely large. So if you were to electrochemically strip out that lithium, it's in excess of 30 milliamp hours per centimeter squared. So with those architectures, then we examined as a function of the nanowire composition, the reversibility of stripping and plating. In this case, germanium was the outstanding performer. You can see that it maintains the longest reversibility, followed by these silicon germanium alloy materials, our silicon at the end, and this is our control lithium here. In a slightly different approach then, so I'm kind of skimming over these, the depth of the research is all in the papers. There's a lot of additional analysis and kind of mechanistic interrogation as well. The idea then was to try and tune this approach a little bit. So using these as an interlayer. So in this case, this is a carbon cloth, which is inherently lithophobic, as we have just seen previously. And we had two scenarios here. So one where you just use that lithium cloth directly on the lithium metal anode, and another one where you coated it with lithophilic wires. So again, this was our germanium, and they were grown in low loadings intentionally onto that carbon cloth that you have here. And they were then placed down on top of the anode. So what you can see here, and I will show it based on SEM analysis on the next slide, is that this encourages bottom-up lithium infilling into that structure. And what you can see from the full cell performance that we have down here at the bottom is that this significantly increases the performance. So this is the blue guy here with your lithophilic interlayer. The carbon cloth on its own, you can see that that dramatically drops off in terms of its capacity. And just based on a standard lithium counter electrode, that drops off much faster. I will point out, you can see here that there are fluctuations in these data. This is before our recent infrastructure upgrade. So these were done in the room temperature. So you can see these really nice periodic daytime features here. So you see these 5 bumps. You can basically use it to track the air conditioning that was on during in the building. So looking then at the ex situ analysis of this, you can see the kind of summary of it is down here at the bottom. When we have just lithium on its own, these are across the top column that you'll see here. And these are the kind of characteristic filament type growth that we see for lithium up here at the top. Okay, so this is your cross section. This is at 2 milliamp hour per centimeter squared. You see that this interface between the freshly deposited lithium and the old lithium is disconnected in the first place. And here it's even more pronounced once you move to 4 milliamp hour per centimeter squared. Okay, so that would explain why we saw significant capacity degradation in the case of the control lithium. For the lithium current collector one, where it didn't have the germanium incorporated, these are top-down images that are shown here. And what you can see is even at 2 milliamp hour per centimeter squared, you have significant lithium deposits on top of that layer. Okay, so this is shown down here schematically as well. So we don't have preferential lithium plating underneath the layer. And these are shown from the cross sections as well. So at the 2 milliamp hour per centimeter squared, shown here with these dotted lines. And similarly here for 4, you have no lithium infilling throughout that carbon cloth here. All of the lithium is occurring on top of the layer. When we moved to including the germanium into that as the lithophilic element, you'll see here at 2 milliamp hour per centimeter squared, that is a filament of the carbon paper. So we are seeing no lithium deposits at the top of that layer in this scenario. And by the time we move to 4, basically we have infilled through that carbon layer, and we still only see quite sporadic lithium deposition on top. And again, when we look at our cross section here, you'll see that you have this nice compact lithium layer that's plated underneath that carbon cloth. Okay, so from these different approaches, what you're seeing here is that we're able to control the location of that lithium plating by incorporating, as I said, quite a low loading of the germanium in there. So in terms of being kind of cognizant of the practical side of things, as I mentioned before, we don't want to be incorporating an enormous amount of additional excess mass into the system. So I guess this is the most optimized system that Saeed was able to create. So we have a very simple approach where we can grow these nanowires directly on a copper current collector. So this is done in a simple hot plate within a glove box. It's through a thermal decomposition of germanium precursor, which is diphenyl german here. And again, we're able to tune the loading that we get on the germanium nanowires. So in this case, it was around 0.2 milligrams per centimeter squared. So again, reasonably low loadings, which would not be practical from a lithium ion perspective in terms of the areal capacity. But here we want to minimize that layer. Again, from the resource side of things, it makes sense for germanium, even if we're not necessarily expecting this to roll out to the gigafactory scale. But what it is a really nice demonstration of the ability to tune these materials and tune kind of the deposition characteristics for these materials. So if we look at the ex situ analysis that was done here, so this on the left-hand side, this is lithium plating and stripping that was done solely in the case of a copper current collector. So you'll see here, this is at 0.25 milliamp hour per centimeter squared. This is at 1, this is at 2. Okay, so again, these are kind of characteristic lithium growth morphologies that we would have seen previously. So they're very non-uniform, they're anisotropic. And again, what you can see from the stripping characteristic of these were then stripped up to about 0.25 volts here, is that you still have significant residual germanium that is present within, or sorry, you still have residual lithium that is present on the current collector. When we compare that then to the germanium scenario here on the right-hand side, what you'll see first is you have this initial lithiation. So that is lithiation of the germanium nanowires. This is with an additional 0.25 milliamp hour per centimeter squared capacity. This is with one, this is with two, and this is with it fully stripped out. So if we compare these directly, so let's say if we compare H to C, you can see that we've really regulated that plating morphology compared to the standard copper. And by the time we get to 2, we've really held back that anisotropic lithium plating characteristic. With J here, I just want to highlight that this is not residual lithium. So what this is this is the starting out germanium nanowires. And if you look at the electrochemical profile that you have here, we have basically only slightly delithiated that. So if we look at the characteristic lithiation profile of germanium, these are remaining mostly lithiated, the germanium nanowires that you have there, which actually means that it's a very stable morphology. So the restructuring that I mentioned previously that happens during lithium-ion cycling, that would usually only be if you fully alloy and dealloy that structure. So in this case, this host is very, very resilient and will not change over time with cycling. And that's why we're able to get this long-term stability in the cells. So comparing then different chemistries, so we have our standard copper as the control here. So these were just plated with the same amount of lithium in each case. So in the purple case and in the green case, the only variable that we have there is just the inclusion of that thin layer of lithophilic germanium in this case. So what you can see is with an NMC 811 cathode chemistry that we have here, up to 2 milliamp hour per centimeter squared capacity, that we have much better capacity retention in the case of the germanium containing anodes. And for the lithium sulfur chemistry that you see down here at the bottom, again, it much more rapidly degrades in the absence of the germanium. So we were primarily linking this to anode changes because the cathodes were fixed in each case. And this is the post-mortem analysis of the plating morphology at the anode side. So this is, again, very uneven. We would have dead lithium that would not be reversible in the case of the copper alone. And on the right-hand side, when we have our germanium included, we're able to, again, really regulate that lithium stripping and plating characteristic. So to change tack to finish out on the dual cation side of things, this is a really interesting area. There are a number of different papers that I think kind of set the scene for this, but there's quite a variation in terminology in the literature. So for example, you'll hear lots of work around dual ion batteries. There are lots of different things that captures. So what we're really interested in is dual cation. So when you have two different cations that are present in the electrolyte, and basically seeing how those interact and how they interact with the active materials. So this is a paper which is reasonably old in this space. So what they were looking at was an LFP cathode versus an sodium counter electrode. And basically they were looking at the influence of these mixed electrolyte systems. Okay, so the actual mechanism here, this was a communication article in 2018. The mechanism wasn't fully investigated. So what they saw in this mixed system, in the red one that you see down here, this voltage shift is just due to the fundamental potential difference between lithium and sodium. But they saw in their sodium hybrid system that they had more reversible cycling, so longer capacity retention. The system that is most linked to what we have looked at, this is work from KIT more recently in 2024. So they chose a magnesium anode and they chose titanium disulfide, which is a very much a classic cathode system. So they had a range of different systems down here. This is at the electrolyte scale. So you had a pure magnesium electrolyte, you had a magnesium sodium electrolyte system, and you had a magnesium lithium system. So the thing to note straight away from the electrochemical response is that they're different. You have voltage profiles which are clearly showing different features over the same potential range here, so 2.4 to 0 volts versus magnesium. If we then pay attention to the capacity, you can see in the magnesium system down here that your reversible capacity is around 40 milliamp hours per gram. Whereas when they had the dual systems, so magnesium and sodium and magnesium and lithium, these were more around 200 milliamp hours per gram. So essentially what was happening is they were getting additional charge storage mechanisms, which for us was a really exciting kind of background idea that we wanted to try and bring into our work. So there's a lot of questions to consider there. So which ions are active? So in your dual ion systems, the magnesium or the sodium are both active, and in which electrodes? So again, in this case, you have a magnesium anode. What is the stripping and plating characteristic in that system? And what we wanted to see is, could they be extended beyond intercalation systems? So again, you probably have plating and stripping here at the anode side, but at the cathode side, you're just looking at intercalation into TiS2. And what we want to see, kind of thinking back to that table that I showed earlier on, is can additional ions, can we unlock new phases? So all of those different theoretical capacities that I showed, they're linked to the formation of specific phases in those dual systems, so where you have just a single charge carrier and the group 14 element. If we move to these ternary systems, can we try and unlock new phases and increase the stability? So as one slide of background, this builds on work where we had sodium ion alloying. So again, in these group 14 materials, we investigated these as different compositions. So we had our germanium scenario, we had pure silicon, and when we had our silicon germanium 50-50 scenario. So as I mentioned, for sodium ion, it's more difficult to try and get these lighter elements in group 14, so silicon in particular, to reversibly cycle. So we did some nice, just a basic analysis of our nanowires. We have pure germanium here, we have our pure silicon here, and we confirmed that we made this nice 50-50 alloy in between. So I guess that the take-home message here from the electrochemistry is that amorphous germanium in a pure sodium ion half cell, basically it gives around 400 milliamp hours per gram, depending on the exact anode configuration that you have. But what you see over time is that this capacity drops off. Okay, so I'll show in a second with the SEM there that this is linked to material-related processes, whereas the alloy in between, which is silicon germanium, is more stable in terms of its capacity retention. And then when we try to cycle the amorphous silicon here, you'll see that we got essentially negligible capacities. So we have no reversibility in the sodium and silicon scenario that we have here. So we wanted to try and understand that a little bit. So looking at the 50-50 composition here at the macro scale, this was the most stable one. What you'll see is that the anode morphology overall is far less pulverized than in the case of the pure germanium. So in this 50-50 scenario, essentially the material hasn't been as impacted by the cycling. So that was kind of laying the groundwork for this dual cation alloying. So what you'd see from this data here is these are two sodium ion half cells, one of which is based on the orange one is an NaOTF degDME electrolyte, and the other one is an NaOTF degDME electrolyte, but also has 0.5 molar LiPF6 in there. So we have essentially identical germanium electrodes, and we have a sodium counter electrode. And what you can see is as soon as we incorporate the secondary charge carrier into the system, we get a doubling of the specific capacity that we can achieve. And also we get a dramatic extension of the reversibility. So this matches what we had seen before for germanium in sodium cycling. But once you bring in these dual ions, we have dramatically improved the performance. So looking at the electrochemical fingerprint of this, then this is your kind of characteristic germanium alloying with sodium. And what we're seeing is the desodiation then is a single feature which shifts over time. In our dual ion system, it's much broader. So you'll see this here in the voltage profile, that you have much more activity over a wider potential range during alloying. So what this hints at here, and we'll show it in the next slide, is that you have more interaction between the two ions as you go along. And then we have two main features then in the de-alloying portion as well. So we did kind of standard rate capability just because every reviewer wants to see these in battery papers, but also showed much more importantly that this is reversible up to 1,000 cycles. So looking at kind of the mechanism side of things here, so we had some challenges around interrogating these using microscopy. You have overlap between germanium and sodium in the EDX energy range. And also we just basically wanted to really prove that the lithium was active in the system. So we did some nice EELS analysis here. And what we found was that we had lithium incorporated into the fully alloyed system, which was removed once we dealloyed it. So through kind of clever experiment design here, this is the differential capacity plot of the profile shown again. And what Saeed did was he took electrodes at various points along this profile and performed ex situ ICP analysis. So what that allowed him to do was basically decouple the ion contributions during alloying and dealloying. So as I said, was hinted at from the electrochemical response, what you see here is during the alloying, they are working together. So you have lithium and sodium ion that are both going into the system at the same time. And by the time you get to the end of this session, or by the fully alloying is completed, you have a predominantly lithium-rich system at the end. So the dealloying one is even more interesting in that, again, you're starting out from your lithium rich that we finished here. And what happens initially is while your overall ions are obviously decreasing as you're dealloying it, your sodium ion contributions are actually slightly increasing. So you see the relative amount of sodium is increasing. So for us, that was a really difficult mechanism that we needed to just try and explain. So I'll show this here on the right-hand side. This was done through a nice collaboration with the University of Birmingham. And what they helped us with was trying to evaluate this triphase system for germanium, lithium, and sodium. This path that you see here is through the alloying, which is shown in red, and the dealloying path in terms of the composition that we were able to extract from that ICP that you see before. So essentially what we're showing is that this initially passes through a chemical environment that is roughly LiNaGe3. Okay, so roughly equimolar there in terms of Li and Na. Then it moves down to this lithium-rich domain that you see here in terms of the formation energy here is low, and then passes back up through nearly to NaGe. Okay, so again, this is the kind of energetically favorable path that this takes through that ternary phase landscape that you see up here. Okay, so this was a nice finding that matched what we had seen from the ICP analysis. And then finally, to kind of round out the study on this, what we took was a sodiated FeS2 cathode material, and then we assembled this in a dual-ion electrolyte system and also in a sodium-ion configuration as well. And what you can see is once you have this dual-ion activity that's going on, you have initially around the same capacity just because of the way that the electrodes are matched, but you've significantly increased the cycling stability relative to the sodium-only case. So just as kind of the second last slide, just to kind of put the context out around these dual-ion batteries and what's next. So obviously we want to understand that existing system even more, so perform new material characterization, do more collaborations to see how we can probe some of those kind of nanoscale processing. I guess for us, the open question really is around the electrolyte. So seeing what is going on there in terms of the ion desolvation, for example, you may have noted that we had differing salts for the lithium and sodium ion electrolyte. So what we want to do is see, can we come towards kind of design rules for these dual cation electrolytes? We're also looking at things like other active materials. So the holy grail, to mention what I said before, would be to try and get this to work in silicon. Tin, again, just from the production side of things, is more accessible than germanium. And we would also be able to compare then in terms of how translatable those mechanisms are. We're looking at alternative electrolyte formulations. And again, we want to boost the energy density. So looking at different cathode materials. So for FeS2, the voltage of that is quite low. So we'd want to bring that up. And then this kind of opens up new ground for us as well in terms of new cation pairings. So could we look, for example, on that system that KIT mentioned, could we look at sodium and magnesium? and try and unlock kind of new charge storage mechanisms and see can these cations basically work together. So for me, just to summarize, I hope I gave a nice flavor for the research that we're doing here in the University of Limerick and the kind of global idea of where these group 14 materials come in. So I'm sure lots of people are aware of them from the pure lithium ion perspective. So showing some of our nice examples of what we're doing here. So looking at our silicon graphite composite materials, how we can use these nanowires as very much model systems to look at how the materials restructure and SEI formation, and then some of the more interesting examples along kind of metal anode development. For the dual ion battery, the fact that we're able to harness these dual lithium and sodium alloying processes specifically in germanium, and we're trying to extend those to see can we unlock these new charge storage mechanisms. And basically, as is kind of the guiding force and all of the research that we're trying to do is to understand these better and give us some new alternative chemistries to play with as we continue. In terms of the funding personally for me is primarily through Research Ireland. And as I mentioned, we have two projects that are funded by Horizon Europe. So with that, I will stop and hopefully answer any questions that might have come to the floor.
Super, thanks, Hugh. And I think I can speak for all when I say that it's